board, and therefore, without further ado, I'd like to present to ask the two presenters of paper number 106, Shayan Mohammadi and Keivan Ghasemi Nodooshan, to go ahead and turn on their presentation.
Hello, everybody. We are happy to present. This is Shayan.
Same here, Keivan. We're happy to start our presentation and get this session going.
Hello, I'm the third author. I'm Dr. Mikoniatis. I'm the advisor of Shayan and Keivan from the Industrial and Systems Engineering at Auburn University, Alabama. Keivan and Shayan, I think you can also turn on your cameras during the presentation.
Okay.
Yes, that is right.
Give us 1 second. I need to switch the video to the screen that has the video ability. Give me 1 second.
So can you see our screen? It sounds like we cannot share our video while we are screen sharing.
Oh, okay.
Yeah. Well, are you guys able to see the video now?
Yes, we see the presentation, yes.
Okay, I'll go ahead and start.
Hello everyone, my name is Keivan, and along with my colleague Shayan, we will be presenting our article co-authored with Dr. Mikoniatis, which is titled A Risk Management Framework via Multi-Paradigm Simulation for Supply Chain and Business Process Management. In this article, we have utilized simulation as the modeling tool to develop a risk management framework for BPM and SCM fields. The motivation for this article was twofold. First, the history of risk management in industry is relatively short and only dates back to the 1990s. Second, the complexity of dynamic BPM and SCM behaviors is beyond the limitations of traditional optimization approaches like linear programming or mixed integer linear programming. When we reviewed the current literature on this subject, it was observed that supply chain risk management literature was mainly focused on agent-based simulation, and that of business process management on discrete event simulation. And in the cases that a hybrid model was used, it is mostly a combination of simulation and traditional optimization methods. With the review, we observed a gap that a multi-paradigm simulation method has rarely been used in the field to the best of our knowledge. To summarize the contributions of our risk management framework to the literature, first, it utilizes multi-paradigm simulation model. Second, it quantifies risk to make it more tangible. And third, it brings risk management and operations under one umbrella as opposed to two disjointed functions. Now let's talk about our methodology. We have developed a four-phase risk management framework of define, model and measure, improve, and sustain. And starting with the define phase, first, the main objectives of decision makers must be captured. Failure rate minimization is one example. Second, risk minimization is added to the objective pool. In step 3, a risk taxonomy is created with the goal of getting to the risk's root cause. In steps 4 and 5, risk severity and frequency matrices are developed. Next, project team is built, and customer requirements and their related quality metrics are defined. In the model and measure phase, first we need to determine which simulation method works best for each object. To do so, we have embedded the Mikoniatis and Angelopoulos heuristic into our framework. Next, we need to calculate the total risk by the summation of risk value of risk J in process I, which is based on the bullwhip effect of process I on the rest of processes, frequency of risk J in process I, effectiveness of risk control of risk J in process I, risk J's residual severity in process I, and its inherent severity in process I. And lastly, the interaction points between the different simulation methods need to be identified in case of multi-paradigm selection. In the improvement phase, the project team identifies the processes that yield the best results when their risk is mitigated. For example, in this chart, an average performing risk control on process 4 in yellow would outperform even the best risk control applied to process 3 in gray due to their respective frequency and severity. Finally, the sustain phase of the framework champions the spirit of continuous improvement. The main ideas are to revisit the model assumptions frequently, update the models based on those, keep the data up to date, and creatively perform design of experiments for the risk control. All these sustaining efforts must be an integral part of a sustainably successful modeling and simulation practice. Now let's further illustrate our risk management framework with an analogic case study. The case studies a supply chain consisting of 16 factories and a distribution center supplying them via trucks. Phases 3 and 4 are not considered as they require decision-maker participation. Starting with step 1, truck utilization and demand satisfaction are defined as the objectives, and risk minimization is added to the objective 4. Next, a risk taxonomy with 8 main risk categories is developed. Each category is then further broken down to subcategories, and tools such as Fishbone and 5Y are utilized to get to the root cause of each subcategory's risks. Developing the risk severity matrix is the next step. Here, risks are assigned a numerical value based on their qualitative severity level that corresponds to their respective effect on the enterprise. Similarly, a risk frequency matrix assigns percentage values to risks based on their frequency of occurrence. Steps 1.6, 7, and 8 are out of the scope as they need direct user input, which concludes the phase 1. Shayan will walk you through the rest of the presentation.
Hello everybody, this is Shayan. I'm happy to present the rest of our article. Frameworks modeling and measure phase starts with applying Mikoniatis and Angelopoulos heuristic to determine what simulation method best suits our objective. We start with identifying a few criteria and variables of interest for our objectives. Heuristic results show that the discrete event method works best for truck utilization and risk minimization, while agent-based method is chosen for demand satisfaction. Here is our case studies representation in any logic environment. We have identified that this case study needs a multi-paradigm simulation. The next logical step is identifying the interaction points between the discrete event model of truck utilization and agent-based model of demand satisfaction, which are demand, request, and product delivery. We developed the deterministic base model for verification and validation purposes. Using parameter variation, we observe the logicality of the model's behavior. The base model flow starts when a factory generates demand. When the demand is received by the distribution center, loading operation starts, followed by a commute to the factory. A truck goes through docking, unloading, and undocking operations next. When demand is satisfied, the truck commutes back to the distribution center and factory state changes to manufacturing. Later, we built upon the base model and added risks. We introduced 2 risks of insufficient workforce and abnormal loading time to the loading process. Likewise, factory demand is in a risk of experiencing high surges. Finally, commute operations face the risk of heavy traffic. Using risk frequency and severity matrices, we calculated the inherent risk value of each risk. Here is risk incorporation in the base model of the truck behavior. We have introduced the risks in the loading process, moving to the factory, and also going back to the factory when the demand is satisfied. Likewise, high demand risk is added to the agent-based model. To do so, we added a new state in addition to the normal state that represents the demand risk. Now that the base model is updated with risks, we built upon it and introduced risk controls. The insufficient workforce risk can be mitigated by having on-call contractors. This control is effective 90% of the times. The risk control introduced for heavy traffic situation is a real-time routing, which is effective 75% of the times. The other 2 risks don't have controls. Lastly, residual risk values are calculated based on controls effectiveness. Here, we can see updated discrete event simulation model with controls. We have a control for insufficient workforce and another one for truck routings. Now that the base model building is complete, let's discuss the configuration and results. The model is run for 70 iterations, each consisting of 5 replications. And there is a requirement that trucks utilization must be less than 85%. The base model utilizes 6 trucks while satisfying the requirement and doesn't incorporate risk. When risk is added, 6 trucks of base model becomes infeasible in terms of utilization requirements. Controls help reduce the total risk value and overall utilization, but still infeasible. It shows that the deterministic decisions of the base model will at best be suboptimal in presence of risk factors. So a non-deterministic re-optimization is necessary to satisfy constraints. The trade-off is adding another truck instead of phasing infeasibility. In conclusion, we created a novel risk management framework for BPM and SCM using multi-paradigm modeling and simulation approach to risk minimization, which is applicable to research and practice. Our approach also quantifies risks of a BPM and SCM, and finally, it's a closed-loop approach to continuously manage risks of SCM or BPM. Thank you for taking the time to read and watch our article and presentation. We would be more than happy to discuss our article and framework further with you if you have any questions or are curious about any part of our article.
Thank you, Shayan and Keivan, for the presentation. We have time for a couple of questions. Any questions?
More than happy to answer.
We'll be happy to help.
John, go ahead, please. Just unmute yourself, John.
Yeah, how do you reconfigure? Can you reconfigure dynamically the supply chain? In other words, if something, if you have a risk management, but then actually something in those factories, you know, the transport from one factory to another, material or something like that, if it actually is interrupted, can you reconfigure dynamically? In other words, send factory 6 stuff from factory 4 instead of factory 2 or something like that.
So that's what we capture in the risk taxonomy step of the simulation. So basically, there needs to be a holistic approach, looking at all the operations, and then using tools like 5Y, these kind of things to make sure, okay, this happens in this what if scenario, we have this approach. And there are some things that you cannot reconfigure, like going to the like strategic and like operational levels of a supply chain. The strategic ones, like, can I move this plant? No, I cannot. But can I add 1 truck? Yes, I absolutely can do so. Or can I use these trucks dedicated to this part of the facility and reroute them to this place that is using like facing a surge in demand or some other problems?
And we have also introduced the concept of residual risk value, which means we cannot eliminate risk. We need to have some level of risk acceptance. Whatever is left, we need to accept the value of the risk.
Did we adequately answer your question? Or
Yes, that's fine. Thank you.
Sure.
Do we have any other questions? I just have, oh, John, your hand is still raised. Perhaps you can unraise it.
I'll unraise it. Lower hand. Okay.
Okay.
It's lowered.
Perfect. Thank you, sir. Thank you. You may have mentioned this in the paper itself, but for purposes of the audience listening into your presentation this afternoon. While you mentioned that you made use of both discrete event simulation and agent-based simulation in your study, you did not explicitly mention what simulation platform you used for your study. Can you inform the audience of that?
Yes, we used the AnyLogic software to do our simulations.
Yeah.
Well, sorry,
it was quite apparent from the figures that you had that you used AnyLogic, but I just wanted to ask you to explicitly state that for purposes of the entire audience.
Sure.
And when you specified the cutoff values for the different categories of risk frequency and risk severity, were these cutoff values based on existing literature, or did you actually have to specify the cutoff values yourself?
I got the cutoff values based on my working experience in insurance industry. I had the exposure to the risks when they were dealing with that, so I got the idea from them. Okay,
so but it's not yet established in the supply chain management literature, I presume.
Yeah, it's not there.
Thank you. All right, thank you very much, Shayan, Keivan, and Dr. Mikoniatis for this presentation. We now move on to
very nice presentation.
Yeah. Thank you.
Thank you.
And very nice.
Thank you for your time, everyone.
We now move on to the second paper, and we call on Christoph Praschl to present paper number 108.
So I hope you can hear me, and I hope that the screen share is also working fine. Do you see the screen?
Again.
Okay, perfect. So I'm going to start the presentation now.
Hello everyone, my name is Christoph Praschl and I'm a researcher at the research group Advanced Information Systems and Technology of the University of Applied Sciences Upper Austria. In my today's talk, I want to present you our paper on the topic of multi-resolution localization of individual logs in wooden piles, utilizing YOLO with tiling on client-server architectures. With the recent improvements in computer vision due to availability of good deep learning paradigms, machine learning frameworks and improved GPU hardware, the automated vision-based measurement becomes visible in many industrial areas. Thus, as an aspect of digitization and Industry 4.0, more and more production processes are now performed in a semi-automated way. However, in forestry industry, for the domain of wood pile trading, key aspects for the price, such as cross-sections of the logs, quality and type of the wood, are most of the time still assessed in a manual way. As this is a very time-consuming process, digitization is a key factor in cost reduction. The present paper is part of the Woodmaster Plus research project. This project follows the goal of inspecting wooden piles using a mobile smartphone application. The application is designed for foresters and forest owners who are interested in the volume-based value of wooden piles. Since neither a network connection nor a mobile device with high computing power can be assumed in a forest, the process is based on a separated client-server architecture. The proposed visual process is separated in multiple steps, utilizing deep learning models, starting with a log localization, followed by the segmentation and classification of every individual log. The classification process is in turn separated in a type classification step and a quality classification step. Combining the determined log information with additional user inputs allows us to assess the value of a wooden pile. The focus of the present paper is on the localization part, while the other parts will be addressed in future works. The log localization has to consider two main aspects. On the one hand, the process should use as few resources as possible, so the performance impact should stay as low as possible, as well as the storage requirements. This limitation can be attributed to the project, which isn't targeting some high-end devices. On the other hand, the results can be improved using an alternative server-side model, which doesn't have these resource limitations. Next to the hardware limitations, the localization process also has to consider seasonal characteristics like front faces covered with snow, dirt, mud, or shadows. This leads us to the research questions. First of all, can YOLO be used in a multi-resolution approach to allow for localization of small wooden logs? Next to that, can consumer smartphones be utilized to achieve preview results in real time that are refined on a server for high quality results? And finally, can lag in seasonal wood log characteristics as snow, mud, or shadows and other weather conditions for the acquired images be compensated by advanced data augmentation strategies? To tackle these research questions, we have searched for adequate datasets. Unfortunately, we couldn't find any publicly available dataset of wooden piles. For this reason, we have decided to create our own dataset based on images of our project partners. This dataset grew to 440 images in total, distributed over all seasons with 42 images recorded in spring, 125 in summer, 97 images in autumn, and 133 winter images with partially snow-covered piles. The season of the remaining images is unknown because of the situation that there was no timestamp available. These images contain over 18,000 logs. Like that, we have 42 logs in average per image, with at least one log and a maximum of 395 logs per image. Next to the seasonal information, we have also labeled the images with bounding boxes for the training of the localization process, with binary masks for the subsequent segmentation step, and classes for the classification process using an own data labeling tool that was integrated in the backend application of our partners. Based on the created dataset, we applied some pre-processing steps as a preparation of the model training. We decided to split the rectangular images of the dataset to multiple square sub-images using a sliding window approach. This step is required because of a tiling process we are using to compensate trade-offs of the YOLO model, but more on that later. Next to the splitting, we are resizing the sub-images to a unified size of 416 times 416 pixels. Finally, we are randomly separating the preprocessed datasets into a training and a test dataset with a 50-50 ratio. To avoid a bias, this separation is done per season. The idea of this seasonal splitting is that we have, for example, snow-covered logs in the training as well as the test dataset. Based on the prepared dataset, we are applying multiple augmentation methods to increase the number and the variety of the training data. To do so, we use on the one hand classic methods as flipping, cropping, or image transformations as translations and rotations, as well as color adaptations according to the contrast, brightness, and saturation of the image. In addition to that, we also use more advanced methods to simulate seasonal characteristics. For this reason, we have developed augmentation functions to apply different textures to individual logs, which allow us to simulate snow, mud, or different types of shadow as a drop shadow effect or a splattered shadow. Using the augmented data, we have created two YOLO models for the localization of wooden logs. Firstly, we are using a scaled tiny YOLO v4 model for the client with storage requirements of only 23 megabytes. Secondly, a classic scaled YOLO v4 model is on the server side with higher storage requirements of 250 megabytes. As mentioned before, YOLO has problems detecting small objects. To compensate this problem, we are dividing the input image into overlapping sphere tiles. This allows us to increase the size ratio of individual logs compared to the image size and allows detecting also small logs. The trained models are evaluated with a sample of 10 pile images with 985 logs. These logs occupy an area of 5 million pixels of the input images. The results are compared with a former approach using Haar cascades, showing that the tiny YOLO V4 model is capable of correctly detecting 82% of the logs, covering 72% of the bounding box area. Compared to that, the classic YOLO V4 model results in an even better log detection accuracy of 94% and a bounding box area ratio of 90%. As a conclusion, we were able to show that YOLO models can be utilized for the localization of logs in wooden piles, both locally on smartphones with low resource requirements, as well as on a server resulting in a higher accuracy, which is a positive acknowledgement of our first two research questions. Can YOLO be used in a multi-resolution approach to allow for localization of small wooden logs? As well as the second question, can consumer smartphones be utilized to achieve preview results in real time that are refined on a server for high quality results? Next to that, we were also able to compensate seasonal characteristics using augmentation strategies, and like that we're able to answer the final question, can lag in seasonal bootlog characteristics and weather conditions for the acquired images be compensated by advanced data augmentation strategies. In the future, we want to further expand the dataset as well as our evaluation process. To do so, we plan to lay the research and development focus on the self-adapting nature of the algorithms. Utilizing existing labeling tools, the results of the deep learning algorithms can be visually inspected and post-processed in a semi-supervised way, and like this should allow to incrementally enrich the training data sets of the models getting sequentially retrained. With this, I'm at the end of my presentation. Thank you for your attention and you're welcome to ask questions.
Thank you, Christoph, for the presentation.
Thank you.
We have time for a couple of questions from the audience. Kirill, yes, please go ahead.
Okay, hello. First of all, thank you for your great presentation. It was very interesting. I would like to ask you some details about data augmentation, image augmentation, and how it was tested or even validated.
I hope I understood your question right. Did he lost his connection?
No, I am still here.
Oh, okay, sorry. We have applied multiple augmentation functions as mentioned in the presentation and have tested this in scenarios with different compared images. So we had the ground truth with real-world images showing snow-covered logs and tried to simulate this visualization of the snow. So we tried different types of textures and using different alpha masks that were randomly created, we tried to optimize the augmentation for the snow, the mud and the dirt. And based on these findings, we also integrated the shadow effects, which were basically in the backend the same procedure, just reusing the alpha mask for applying the shadow effect.
Okay, perfect. Thank you.
Thank you.
Any other questions from the audience? Praschl, Christoph, from your interactions with the players in the forest products industry, have you noted any significant interest on their part to look into the possibility of applying YOLO in their operations?
Our project partner who was involved into this paper, who did this former implementation with the Hakka states, is already implementing this fundings into his smartphone application and is currently using it in his forest industry company in combination with additional partners. So the companies using the application and the results of the paper are raising.
That is, of course, wonderful to hear. Thank you.
Thank you.
Do we have any other questions from the audience? Hearing none, I would like to call on our next presenter.
Today, I would like to give a presentation on interoperable simulation for space logistics and operations for a moon base. These are the objectives of the current project. Diffusion of cheap yet high performance computational solutions contributed in diffusion of simulation in different fields. Indeed, nowadays it is possible to address near every problem by means of models. In particular, it is evident growing interest to this approach in different industrial fields. However, interoperability of these models in framework of systems remains insufficiently covered from the technical point of view. In fact, while it is possible to regulate formats of data and units of measurements used in system of systems. In this paper, the authors propose an interoperability gateway developed to address this issue as well as case study in which the solution is tested. We choose such frameworks and very interested about Artemis mission. Now we see about Simulation Explorer experience. Its SEE program is focusing on space exploration mission, such as construction of moon base. And in the last year, we did an interested topic mostly related to simulation of Artemis mission. Here we discuss about Artemis mission. In the next slide, Artemis mission is mainly focusing on bringing humans base to the moon. In several phases with increasing complexity, this project is involvement of different types of vehicles such as launching system in the ground and gateway of the orbit around the moon, up to lunar landers, rover, and auxiliary systems. In this mission, there are different entities and stakeholders. It is not easy to simulate all the new things in an interoperable way. Consider this means high-level architecture, which is an interoperable standard. We are going to high-level architecture defines mechanisms, procedure, and formats related to data exchange. For instance, it addresses registration of participants, entities, and their parameter, time management, and facing control over execution and interactions for the interoperability. Let's go to the deeper into the details about single components and data exchange. In the next slide, RTI, runtime infrastructure. RTI is the key component of high-level architecture in technical terms. It's required to handle procedures related to data exchange. Here, high-level architecture standards is conceptually clear and complete. There are some problems with RTI implementations because it supports poor programming languages like, but we use only Java and C++ because they have native implementations. Let's go deeper into the details of architecture. Here we go with general architecture of the project. In order to describe the work which was done, in this slide, we represent the general architecture of the system which we are working on. As a key component on the top, we can see RTI, which I had described in the previous slide. In our case, which is pitch RTI. Now to it. We can see some fed rates which are provided by the organizers of the initiative. So there are essential federates required for the execution. Of course, there are other participants from other universities globally who connects their federates and their models. From the RTI block, we decided to connect them with our interoperability gateway. So it's like a federate, like any other federates, and the difference is that it doesn't perform any kind of operation like simulation or elaboration by itself, but it works as a transceiver for other systems and applications. Here, interoperability gateway handles bidirectional decoding, encoding, and forwarding of federation objects like physical entity, reference frame, etc. Now, in our case, the main application is for testing is ARIS rover, which represents in the next slide, that is graphical user interface, the gateway GUI. The graphical user interface is implemented in JavaFX, and it allows to manage connections and to view the log of operations. Here I go deeper into the details of what we did actually. First of all, I present you graphical user interface of the gateway, which was used for testing. It shows all important messages which are used for testing to get the final solution. It allows to filter the messages by type or importance and shows the actual connections. That allows one to choose from predefined RTI addresses on logs of these operations. Here, the gateway used to connect our federates to the central RTI, and on the next slide, we will see the example of such exchanged messages between the gateway and the federates. Here, these are the exchanged messages between the applications and the gateway. Those are in the JSON format. As you can see in the slide, the messages are displayed and structured in JSON format because it's very fast and easy to encode, decode, and also debugging in case of any problem arises. Example, one of the messages in correspondence to different operations such as registration of objects, update of the spatial state, time management, execution, and execution of configuration controls, and so on. In the next slide, I show you the models which are used to test our gateway, that is rover and the base station. These are the models, multiple models are developed to support testing of the system. The most interesting model is our ARIS rover. ARIS has robotic arm manipulator, which requires precise sharing of its spatial data in order to be correctly interpreted by their federates. In the next slide, you can see now it was actually tested and executed. In the next slide, we see about testing and results here. For testing, we used distributed observer network, that is DON environment. It is used for visualization of models provided by NASA organization. On the right, you can see actually our window of our simulator of our model, which is running on local machine in Unity environment. The Unity environment is connected to central RTI by the gateway. Thanks to the gateway, because it remains all, Unity has all native implementation for the pitch RTI. That's the reason we used the gateway. In the image seen in the both environment was exactly same, confirming correctness of data, coding and decoding and exchanging of data. Let's go to the conclusion. Next slide. The proposed approach is an effective solution that is capable to support decision makers in different aspects, from traffic management to emergency situation forecasting. Furthermore, the platform is open to extensions and to possibility to add further components. Indeed, special auxiliary tools developed by authors allow us to define easily the scenario to run simulator on different locations around the world. The preliminary verification of the model was performed by implementing some critical methods by using unit tests on critical methods, as well as by using static code analysis, integration, and some beta tests performed during the execution. As anticipated, currently, the simulator development is in validation phase, which is quite complex, considering number of included components. Considering this, the proposed solution results are very promising. That's it. Thank you everyone for giving this wonderful opportunity. Have a great time.
Thank you, Barath. Are there any questions from the audience? Any questions? Kirill, you are a part of this study, is that correct?
Yes, I was a team leader of General University team this year and last year, and yes, we worked together on this project.
Which university?
Genoa.
Genova, and which other university are working on the project?
Well, it was Facens from Brazil, which was one of main team which we contacted, Munich Institute, Bordeaux Institute, and other organizations.
So it must be a challenge to have to interface with a number of different institutions, but for the magnitude and scale of this project, I guess it is something that you need to work with.
Yeah.
So what are the major challenges that you have identified from your own viewpoint?
I think main challenge is for new participants to establish work relations with other teams, because apart from technical interoperability, we need also to coordinate all the work, plan common actions, and so on. So I think that actually most challenging part is not technical one, but human one.
Understood. I see that John has a question. John, please go ahead.
Yes, it seems as though the rover is a kinematic simulation in Unity 3D. But I was just wondering, is there any idea to put something else like dust or wind velocities? Well, I'm sorry, I don't know if there's a lot of velocity on the moon, but you know, whatever, or actual the photovoltaic aspects of it. I mean, the power supplies and things like that. Can Unity handle something like that, like the power supply calculations, real physically physics and stuff? Yeah.
Yes, we can of course handle power calculations as well as other calculations, and some of them are already implemented. Regarding dust or other particle effects, it's more complex because in interoperable simulation we need to share somehow this information. So or we need to share 1 billion of points of dust, or we need to do simplification, which we will need to lose of coolness of the picture, let me say.
Real simulationists only Only share, well, only if you go under 1 trillion points of dust, you know, you're not really a real simulationist. That's my sense. Okay, but a lot of them are. Okay, thank you very much.
Thank you.
Thank you, Barath and Kirill, for the presentation and the discussion.
Thank you very much.
So now we move on to our fifth presentation for this afternoon. John Richardson will be our presenter, our next presenter. Go ahead, John.
Could you unmute your microphone, please?
And maybe you can unraise your hand, John, if you don't mind.
I'm actually sharing. Let me see if I can put this thing. Can you hear this? Hello, my name is John Richardson, and I'm here to present a paper verification of a naval logistics simulator prototype at HMS.
We hear it, John.
Now, what happens if you have a system under test that's delivered as a black box? What do? Composer's not a complete black box. It has some documentation. It's delivered along with a suite of other optimization research systems and several simulators. And it's basically optimizing the stochastic traveling salesman problem under uncertainty, which is threats and disasters. It's also a black box in virtualization. Composer is a Java app inside of a Docker container. So when we planned a verification process from the Sargent and Robinson references for black boxes, we need to determine the inputs and outputs, additional information, requirements. Fortunately, we have the source code for the GUI. We also have build instructions for a primitive API, plus a user's guide that is reasonable but not good, plus an actual operating simulator to do the acceptance testing on. It's designed for logistics plans and has a GUI that creates logistics plans. What are the requirements? Well, we have no official requirements. So in this case, the GUI is the key for verification of Composer in this situation. The user guide and GUI helps. The optimization code has no source, and so the core algorithms are hidden. We think it's machine learning and neural networks, but we cannot profile the algorithms. Use the GUI optimization metrics and the developer user guide to create requirements that make sense. Then create scenarios, run the scenarios, try the metrics, and then see if we can do better. So reverse engineering the requirements. So they should really be realistic. So we have characteristics definitions for logistics. The GUI should allow the definitions to be assigned values. The GUI should display the metrics, prove that the algorithm, optimization algorithms are appropriate and they're novel. So reverse engineering the requirements continued. They should be useful. The GUI should be intuitive and useful for a logistic planner. It should have icons and it should have useful asset types. The GUI should suggest alternate optimization strategies, and the GUI should display plan simulation results metrics. So let's continue. Let's actually and it should be useful for the logistics community. So let's create a scenario. Now, this is the GUI that we're using to tell, oh, is it useful? So you can see the assets and you can see the an example. So we continue, create a full baseline scenario, and then we turn the game loose. Then what happens is after the game is finished, this is what we have. And it shows the results of the game, and it shows where everyone is at the end of the game, and that will show you instances of how to protect your assets and try and optimize them. So if you need, if you're doing manual verification, optimization, which is needed in this case, first of all, you run the game, it produces a summary. Then in these, you have mission impaired, and then safety threshold, which is risk. So mission impaired means logistics problems, and the risk is safety. So you change the plan by changing the logistics for a ground asset to be resupplied. You run the game again. You know that now the mission impaired and the safety threshold is going down. You repeat this for another asset, and then you run the game again. You've noticed that you're getting better, and you keep on doing this by continually optimizing the logistics resupply process. And then, as you notice, we keep on getting better and better results. So you keep on going until you just about get down to a point where you really can't optimize very much more. Now, this is designed to actually generate automatically plans. Right now, if you have problems with the starting baseline, the generation of automated generation can take a long time or just simply never return. So here's the heat map, which is basically what types of threats exist for the logistics assets. So if they enter any of these areas, they could be destroyed or hindered or delayed. And that's one thing that you want to have better. Okay, so the conclusion is, verification can be done confidently if the system under test has reasonable documentation and you can get derived requirements. This is an almost black box, can be difficult to generate bug reports because we cannot map to official requirements and we don't know the expected results. But we can find bugs, no lat long lines on a map in a Navy simulator, other things like as DVD, database documentation. Validation is nebulous due to derived requirements. You can never guess in an acceptance test whether you got the correct derived requirements. If they make sense, it's as good as you can get. Accreditation is essentially impossible because we have a minimal API. And by the way, you have no real requirements. Now, what this is saying is the black box verification may require significant manual verification, depending upon the initialization of the original plan. The composer GUI could be used for minimal verification testing. We've proved that. The acceptance testing proved that, and the verification process needs to have a backup verification plan. as they say. And then, as you can see from this, these heat maps are partially related to the types of scenarios that you have and the way you optimize the scenarios. So the heat maps will tell you, will give you a good idea how to schedule and route your logistics and when you try and reduce the risk. Okay, at this point, we're ready for questions, and thank you very much. This is John Richardson from the Naval Information Warfare Center, Pacific, signing out.
Thank you for your presentation, John.
See if I'm trying to end share it. There's your shared window. I'm gonna stop sharing. Okay.
All right. Do we have any questions from the audience? Konstantinos, please go ahead.
Hi, John. This was a great presentation. A question I have is, have you considered assessing the model in the delivered methods? Because I noticed in the last slide, if you can load it, I don't know if you have the presentation. In the last slide, you mentioned that the validation is really hard to be achieved. So I was wondering, have you considered using a sensitivity analysis, for example, with different options for delivery to assess the model?
The answer is that we only had it was very, very difficult to get the derived requirements, and so it was very, very difficult to set up enough experiments for sensitivity analysis. That's the main problem with that. In other words, you're essentially given, especially since the actual optimization algorithms, they seem to work, but the problem was that we didn't have the source code. We know from examining the source code, we have the source code, so we could examine it, and we know that they're using some sort of neural nets and convolutional neural nets, but we don't exactly have any way to guess how to, as I said, profile the algorithms. So it's very, very difficult to actually sort of like you can try and do sensitivity analysis, but you never have a real way to prove that your sensitivity analysis is even remotely correct. I mean, that's the problem. It's a black box.
Thank you.
And that's quite understandable, John.
Yeah, thank you.
So,
one more question, sorry.
Go ahead, Konstantinos.
I may miss that. Did you use a specific software for developing this this tool or model? Did you use a specific software tool?
The software tools, it's a Java application. So you got to remember, I'm the tester. I just got this thing dumped on me. Well, and so I've been able to figure out that it's a Java application because it is a Java application. It's stuck inside of a Docker container. So you've got a layer of virtualization, and we have the source code. Okay, so what we do is we can try and understand the source code So we have tools to understand source code and things like that. So you have compilers, things like that. Considering that it was made for a Linux system, it was tested on a Macintosh, which is really BSD Unix underneath, you know. So, you know, there's all the, you know, the profiling tools, but if you have to reverse engineer the Java classes, that's pretty tough, you know.
That's right. Thank you.
Thank you. John, are you raising your hand again?
Yes, I'm always raising my hand. Now, it's almost not a question because earlier at the plenary, they were put up a slide that said there was going to be an award ceremony tomorrow, and that there would be a virtual party or toasting, you know, and I just thought I'd let you know that when that happens, I will be using my simulation team refrigerator magnet, and on the back is a beer bottle opener, so you can tell Augustino and Francesco that I've got everything covered for the party, okay?
Wonderful.
I want one.
It's an antique.
I
So
will ask one of it.
thank you very much. That's about it. Okay, I'm done.
Okay. Any question from the rest of the audience? Konstantinos, please go ahead.
Hello, nice presentation. So a quick question, did you also consider variation for loading and unloading times for the ships in the stochastic model?
Yes, but I didn't present the result in this paper.
Okay.
Yeah. The point is that the production cannot stop, cannot change too much. So all the stochastic possible event that can disturb the transport will be taken into account.
Thank you.
Thank you.
Are there any other questions? I see no other hands raised. We are 15 minutes over the time that we were allotted, but it was 15 minutes extra time well spent because we have had 6 very, very interesting presentations by our presenters this afternoon. This particular session is unlike most of the sessions in IMMM in that there are 6 presentations that are scheduled in a 90-minute period, and then of course we went beyond the 90 minutes, which is quite understandable. And in this case, there are 3 component conferences that are involved in the session. One is EMSS, the other one is HMS, and the third one is MAS. But all of these papers deal with modeling and simulation in supply chains and logistics. So on behalf of the IMMM organizers, specifically Professor Agostino Bruzzone, Professor Yuri Merkuriev, and Professor Francesco Longo, and the chairs of EMSS, HMS, and MAS, I would like to thank everyone for attending this afternoon sessions and listening to all the interesting presentations. I also would like to thank Mohammad in particular for facilitating our completion of this session by helping with the situations where the presentations could not be immediately loaded. Thank you, Mohammad.
Thank you.
So thank you once again to everyone.
Thank you.
I wish you all
for coordinating.
I wish you all a good evening, and we'll see you in the succeeding sessions. Thank you.
Nice day. Thank you.
Thank you.
Thank you.
Thank you very much. Thank you. Bye.
Thank you, Yuri.
Thank you.
Thanks,
Bye.
everyone.
Thank you, everybody.
Have a good rest of your day.
Bye.